Good morning, good afternoon, Americas. Good evening, Europe, Africa, and Asia, and possibly even good night. My name is Rob Urselman, and I'm your moderator for today. I come with 25 years in well engineering and technology development in oil and gas, geothermal, and renewables R&D. These three overlap in the quest to drill ultra-hot rock for geothermal exploitation. Today, I'm have the pleasure of chairing a panel consisting of Mark Russell, CEO of Hypersonics, Igor Kosic, CEO of GA Drilling, Paul Deutsch, CEO of Foro Energy, Jan-Jette Blanger, founder and CTO of the brand new startup Canopus Drilling Solutions, William Bill Mooney, Chief Scientist and old veteran at display of Tetra Corporation, and Raphaël Souchal, who's joining us from France, Director of Drillstar Energies. As we have already heard in earlier panels, heat is king in geothermal. The higher the temperature, the more efficient the whole heat process becomes. So we aim to drill to deeper, typically harder rock in, by definition, a hotter environment. The ultimate objective is to reach ultra-high temperatures by drilling in deep formation. Wells in the order of 10 kilometers, 30,000 feet, and 300 degrees Celsius, 6,000 Fahrenheit and beyond. But we won't get there all at once. As we already heard on Monday and yesterday, there is a commercial staircase via low and medium heat and thus depth. Technically, both oil and gas and geothermal have already been a long way there, but these wells were expensive, often very expensive. To make it economical for geothermal, the wells must become a lot cheaper. This session is the first of two on how we might get there. Tomorrow, in the Future of the Well session, we will hear how existing and incremental oil and gas expertise, tools and methodologies can be immediately leveraged and improved to enable a variety of geothermal concepts. So please hold your questions relating to casing and completion design, HPHT cementing, rig automation, process optimization, learning curves, etc. until tomorrow. Today, in this Future of Drilling panel, we will focus on the sharp end of the stick, making hole. As we get deeper and hotter, apart from the temperature challenge, rocks under those conditions become ultra-hard. For nearly 100 years, drilling has been mostly done rotary mechanical, and this is still evolving at a steady, strong pace. What most oil and gas drillers out there might not know, however, is that PDC bits, now responsible for over 95% of the global footage drilled, are a direct result of earlier geothermal R&D funding. Likewise, the origin of novel hard rock rotary bits such as Baker's Chimera and Schlumberger's Stinger bit originate in the geothermal scene and funded R&D. Now, 50 years ago, the crew of the Starship Enterprise introduced many of us to altogether new technologies. There was the currently still science fiction teleportation, but there was also wireless handheld communication, user-friendly computers, voice recognition, non-invasive imaging, ion propulsion, force fields, and phaser weapons. Some were based on already existing fundamental R&D. Others, however, were completely fake, but drove new inventions now deeply integrated into our daily lives. Mobile phones, personal computers, and medical imaging are all attributed to Star Trek by their inventors. TRIS, the theory of inventive problem solving by its Russian acronym, analyzed many thousands of patents and derived trends of evolutions in systems development. One of these tells us that systems will increase segmentation and use of fields. We went from a knight in shining but heavy and inflexible armor to chainmail, body armor, and right now we're looking at dynamic or electric armor that's proposed for the protection of ships and vehicles from shaped charged weapons. It's the same at drilling. We started digging by hand, then hand tools, then percussion hammers drilling, then rotary bi and tricones, and now PDC bits. Directionally, we went from uncontrolled to whipstocks to bent motors and now continuous rotary steerables. In well control, we went from uncontrolled to a complete portfolio of managed pressure drilling methods. And in casing design, we went from highly tapered to monobore. With my background, I have to mention these. We went from digging a water hole where we lift with hand tools to drilling ultra-deep HPHT wells far offshore in hostile weather and ultra-deep water. we are pushing wells out further and more complex than ever before. We can do that again with drilling for depth and temperature. This is nothing we haven't done before. The existing drilling methods are most certainly still improving, but it's evolutionary, not revolutionary. It's time for a new S-curve in making whole. So it's my pleasure today to have the 6 people that I introduced to you early. And I would give each of them 3 minutes to explain their interest in geothermal and also their background and the fundamental principles of technology. So I'd like to start with Mark Russell from Hyperscience. Over to you, Mark.
Okay, hi. Thanks very much, Rob. Thanks, Jamie, for putting this together. With this projectile and this projectile and millions more like these projectiles, Hyperscience is revolutionizing deep, low-cost drilling for geothermal, as well as applications in the tunneling business. I'm Mark Russell. I'm the CEO and founder of Hypersciences. My background is aeroastro engineering, as well as my family's in the mining business. I was lead engineer for Jeff Bezos, Blue Origin, Amazon, leading crew capsule development, and I left to create a company that revolutionizes the use of hypersonics to fly projectiles into rock at hypersonic speeds, which radically changes how one can drill a hole. What we have been doing with Shell and another major world-class mining company is developing a drill that allows us to drill at cost points that are an order of magnitude lower and potentially 10x faster than today's current drilling technology. The way our technology works is as a rotary bit is turning, we call augmented hyperdrill, we fire projectiles through the middle of the drill bit where they break 70% or more of the rock and pulverizing it into small materials that are brought up in drill cuttings. We use conventional drilling rigs and technology, but we go substantially faster, change the game for the low-cost access to geothermal heat that we're looking for. That's what I founded the company on, and we look forward to demonstrating this in our field trials that are ongoing now in the mining business that are applicable to both the energy sector as well as the mineral sector. And beyond that, we'll run the same similar tests in the tunneling space, participating even in Elon Musk's tunneling challenge that's coming up. So Hyperscience is revolutionizing the speed at which we can drill by pulverization with hypersonic impact with millions of projectiles.
Okay, thank you, Mark. Igor, over to you.
Hi, my name is Igor Kosis, company Geothermal Anywhere, GA Drilling. My background is electrical engineering, and all my co-founders have the strong scientific and technology background. I started my career in the area of electrical engineering, IT, artificial intelligence in the harsh environments. And then 15 years ago, I was fascinated by the potential of the geothermal energy. And we started to look why it is not possible to make it happen anywhere. And we found that there are, of course, a lot of obstacles, but the biggest one is the drilling. And then we started to work to find a totally new concept that will be able to make it significantly or revolutionarily better. We spent first 5 years of the company running with fundamental research, knowing the physics about the potential different thermal and non-thermal technologies. And then in some 2014-15, we started to work closely with the drilling industry, means also oil and gas. It was a very good lesson learned because we found out that to make some success, we need to have a very good test facility, and we created a center of excellence, being able to help us with the high pressure, high temperature testing. The result of our work was the technology based on plasma. Shortly, just to imagine that you have the stream of very hot media that is directly influencing the rock, and the rock, even any other material like a steel, is crumbling into the small pieces. And that was then the work last 3-4 years to combine this very fast technology that can work order of magnitude faster in a hard rocks with the conventional equipment and rigs to be able to deliver the full concept solution. So that's why we also last year we joined forces with operators, go to the field trial, and being able then to prove it in the next months and years in a practice. So that's our history, and we are looking forward for a nice discussion today.
Okay, thank you, Igor. Over to Paul Deutsch, please.
Thank you, Rob, and thank you, Jamie, and the rest of the people organizing this event. We're pleased to participate, share what Foro is doing in this area. Our original project when we got started 10 years ago was around using lasers for drilling hard rock for geothermal. So we're excited to be back and talking about this subject now with everybody else. And our company is focused on commercializing high power laser applications. And for a calibration point, what we define as a high power laser is something in the order of 20 kilowatts or 60 kilowatts or higher, as opposed to milliwatts, lasers, power levels, reservoir monitoring. We have kind of three types of people in our company, which I think is critical to the successful introduction of any novel drilling technology, and that's a combination of people with oil and gas backgrounds, as well as the new technology that you're working on. So, for example, I come from an oil field services background, but I've worked alongside people from the high power directed energy weapons background the last 10 years. And one of our key success factors for realizing this technology is letting the oil field people learn about lasers and letting the lasers people learn about the oil field. The idea of using lasers in the oil field and specifically for drilling has been around for several decades. I think it's important to appreciate some of the advancements in laser technology themselves that make this now plausible. The development of the fiber laser, which is really replaced most conventional cutting and plating for additive manufacturing parts, has driven the costs of the lasers down exponentially, as well as the efficiency, the footprint, and the reliability and robustness. And that combination with fiber optic cable technology that's been used for data transmission and reservoir sensing, pressure and temperature, really makes it possible for this to come to the industry today. Foro has introduced additional innovation that allows you to transmit that power. And we have a set of optomechanical components system that allows you to transmit that light from the surface to downhole. The laser is on surface. It goes through a fiber optic cable that goes to a connector and then an optics pack that shapes the beam. Specifically for hard rock drilling, when we got started, there was a lot of academic work prior to.
Paul?
Yes.
Let me just stop you there on the 3 minutes. And also, can you adjust your headset because your audio is actually pretty bad,
yeah,
so
I
we can actually
apologize.
hear you a little bit better. Okay,
yeah.
thank
So
you.
We'll
come back to you. We'll come back to you later, Paul. We'll go back for the introduction to the next lot. Jan Jette, you're the new kid on the block, so please introduce yourself.
Yeah, hi Rob. Thanks for the introduction, and hi audience as well, wherever you are. It's really great to be here. Yeah, I enjoyed working with Shell for about 20 years, and I've been leading a research and development group for drilling automation and extended reach drilling and zonal isolation there. We did many things. We looked at rotary steerables, software rotary systems for the mitigation of stick-slip vibrations, and also we worked on abrasive jet drilling. Abrasive jet drilling is what I'm focusing on now as well. Is based on eroding the rock away with a high velocity particle laden jet in the jet bit. We call it a bit, but there's no mechanical interaction there. Abrasive jet drilling is great. It has a great rate of penetration that has been proven already in the field before I was born, and that's quite a while ago. But it has always been a blocker, the thing that you have to circulate a reasonably high particle content through the well, and that causes ECD problems, circulation density problems, etc. We solved that at Shell by developing a downhole recirculation solution. The result of that is that you only have a high concentration of the particles at the place where you want to have the erosion, that is at the hole bottom, and the rest of the system hardly sees the particles themselves, which is great. I left Shell 2 years ago, and I founded drilling Canopus drilling solution geothermal last year. So indeed, a fresh kid on the block. I can use the downhole recirculation solution that was developed at Shell, and I have been adding the directional control to that system. Later on, we'll come back about to integrated solutions, I hope. But I think it is essential to have the directional control added to the abrasive jetting technology, including the downhole recirculation. And now we can drill 3 to 6 inch long multilaterals, which is 3 to 6 inch diameter, and then kilometers long multilaterals, which is ideal for the productivity of geothermal reservoirs. There has to be a breakthrough there, and there has to be a cost reduction, which has been mentioned several times already, of about 60% or 70% on the drilling cost of the subsurface structures. My interest in geothermal is that at this moment only a fraction of the subsurface is currently suitable for geothermal development. There has to be a major change in this in order to get close to the targets, the geothermal production targets for the Netherlands, Europe, but also I think worldwide. And I think the directional abrasive jet drilling solution can make that at least 10 times more reservoirs become economical, and that's a breakthrough, I would say. Thank you.
Okay, thank you very much, Jan Jette. Bill, you're the veteran of this panel, so please unmute yourself and give us your introduction.
I'm Bill Money, Chief Scientist of Tetra Corporation. We've been in business 43 years, and we're specialists in pulse power. We used to do a lot of defense work in pulse power, but then in the late 90s, we shifted into drilling. And we've been focusing on commercial applications of pulse power into the drilling technology. The particular project that we're involved in right now, we've been at for 18 years. And we're involved with a service company and 3 different operating companies. It's a all-electric drilling process, has no moving parts, uses conventional rig, and it's been well demonstrated in the lab. We're now moving into field trials. So we think this has a lot of potential for geothermal because it's very fast in very hard rock, and that's exactly what we need in geothermals to cut the cost of drilling.
Okay, thank you very much, Bill. And then last but definitely not least, Rafael Suchal. Please unmute yourself, Rafael.
Thank you, Rob. Thank you, Jamie. Thanks for inviting me here. So my name is Rafael Suchal, as you mentioned, and I joined Drillstar about 10 years ago, coming from another small tech company called Schlumberger. And what I'm going to talk about tonight is another small tool that looks like this, and that's called the mud hammer. So the mud hammer, as you can see or cannot see, is composed of 2 parts. You have the big tube here. That's called a hammer. It's in fact a high power hammer capable of giving very high powerful blows. And then you have the second part, which is here, which is the drill bit. So it looks like a very conventional tool, conventional drill bit, but definitely there's a lot of research and science going on there because we've been developing the hammer for the last 10 years or so. And a lot of time has been spent on the bit itself, because it's not the same thing in drilling with impact with percussion at surface level or 100 meter deep, and doing the same thing 1,000, 2,000, 5,000 meter deep. So this project originated with oil and gas, and we pivoted about 2 years ago to geothermal drilling, and especially, of course, HDR and EGS. So these are the systems which require a lot of drilling in deep igneous rock, where percussion is especially effective and is proven to be a very effective mode of drilling those rocks. This dates back to years and years. Actually, what we've done during this research is prove first on the bench. So we do have access, and that's our chance. And as Igor mentioned earlier on in this discussion, having a dedicated test bench available is a very important point when you develop a drilling techniques. And we do have one from the Paris School of Mines right next door, which enabled us to do a lot of oral testing and then move into field tests. And right now we've performed quite a number of field tests. In fact, I mean, we just finished today one test on a real drilling rig, so drilling with the hammer in 8.5 as we would in a geothermal project. And the goal, as you may know, this is the future of drilling, but this is the really near future of drilling. The technology is almost ready. We have tested it repeatedly in the bench, we're testing it in the field, and we're ready to go commercial. We even started bidding actually on a project in Germany run by Ever in Geretsried. So I'm very excited to talk about you today for the future of drilling and the new ways of making hole.
Okay, thank you very much there, Rafael. Okay, we'll go through a set of questions here before we open up to audience questions later on. For those in the audience, please start entering your questions if you're not already. I'm sure you're already going full at it. We'll try and answer as many as we can today, but it'll no doubt there'll be many outstanding. For those that we cannot answer today, we'll try and get the questions to the panelists and see which ones can be answered, and they will then be posted later on our website. So do ask all the questions you have. First, Paul, hopefully you've got sorted your headset, because the first question is coming to you. So, one measure stick we have for drilling efficiency is the mechanical specific energy, or the MSE, and probably when you start laser drilling, the mechanical is going to fall off. So we're just going to talk about specific energy, that how much energy does it take to take a cubic inch or cubic centimeter for us on this side of the pond out of the rock. In fact, when I think of laser, evaporating rock takes an extremely high amount of energy. So how much energy does it take? And how do you get all that energy down this hole?
Yeah. Hopefully you can hear me okay. So great question. And there's been a lot of prior work to our company measuring laser energy and radiation on different various lithologies of rock. So there's some very detailed SPE papers that I will reference the audience to, but essentially it takes several kilowatts to remove a certain volume of rock. And if you look at the traditional specific energy, they do look at how much per lithology and compare it to ROPs of conventional measurements. And I think that was a good starting point for our company that demonstrated that the power levels are there with light to remove it. In fact, we don't evaporate the rock or melt the rock. We use thermal spallation because, as you mentioned, we require a lot more energy and be an efficient process. So we start with multi-kilowatts on surface, which has about a 50% efficiency from electrical wall socket. We transmit over a fiber optic cable, and then we heat up the rock to remove the compressive strength by thermal spallation, and then we scrape it away and heat the process up. Okay,
thank you, Paul. Similar, Mark, you using a completely different and inapproachable, what the driller, if I stand on a conventional rig there, does that as well. Compatibility with existing rigs and system is always a major issue. Your system brings these projectiles down the holes and needs to be shooting out. When I look at your website, you get thousands of these projectiles through a BHA. It doesn't look very compatible with an existing drilling rig and practices that we're used to. So how are you going to get operators, rig contractors, and drilling crews on board?
Well, that's a really good point, Rob. So what I'm holding in my hand is a small, what looks like a paintball. And what we do is we pump small projectiles all the way to the bottom of the hole continuously. And so think of it as another additive into your drilling mud. Everything's done, all the energy is applied down at the bottom of the hole, including your fuel and your oxidizer. So you're using really simple chemistry, air, natural gas, air, and diesel. So the rig operators are already used to using these types of fluids. What we do is we combine them down the hole and create this immense opportunity for rock breaking. The compatibility is simply putting the ability to meter out these small spherical projectiles down to the bottom of the hole, where the system takes care of the rest of it in the bottom hole assembly. So the complexity is a bit of rocket science, but it's all at the bottom of the hole. The rest of the operations are relatively conventional. So either you can deploy it as a conventional pipe, or you can do a coiled tube solution. Conventional pipe is obviously more typically used, but we think the opportunity to do coiled tube is really amazing and could be a game changer for adoption to the industry.
Okay, thank you. And then Igor, this comes also, just the same question, and it comes from the audience actually already. It's saying the plasma tool is said to be completely compatible with existing drilling rig equipment. Can you elaborate on that a little bit already? And again, how do you get these vast amounts of power down the hole that you need?
Yeah, thank you. So for the plasma drilling, how we are working, firstly, we are also considering evaporation as melting, as you mentioned, but these are the processes that are extremely intensive for the energy. And we are using currently the pulsed thermal spallation effect. It means that we are working in a very short, target is to work in a very short intervals and to be able to destroy the rock in an efficient way, let's say regardless of the depth or the pressure that we are working in. And regarding the infrastructure, that what we need for that, we are focused firstly on the cold tubes. It means that our strategy combining the conventional and the plasma drilling is one of the cornerstones, as we want to utilize as much as possible that is on the in the existing industry market. And cold tube has a super advantages, like we can be fast. Our target lifetime of the tool continuous work is set to several hundreds of hours. So without need of the tripping from the need of the maintenance of the tool. And also now we are working on the solution that can fully use the rigs from conventional, or what we see as a target, at least for the first years of the projects, is the hybrid solution, when we can drill through the soft sediments at the top with a conventional, and then being able to apply the plasma once we will hit the down harder rock. And of course, what is here interesting, that our focus is for the harder rocks, is that the harder rock is, then the faster and better results we have. So that's some anomaly to the classical mechanical drilling, that for us then to drill deeper and deeper is considering the rock strength is better. So this is one of the parameters we achieved, also already proved.
Okay, thank you. Bill, would you want to add to this for your equally unconventional system? How do you get the power down? How compatible is it? And how do we get things like cuttings out of the hole? Do you create cuttings? You might want to unmute yourself.
Our process creates miniature lightning bolts inside the rock 200 times a second. So we're failing the rock in tension. We use conventional drilling rig to manage the bottom hole assembly and to sweep the cuttings out. So from an operator standpoint, it looks pretty similar, except it's drilling really fast. We generate power down hole, and this will get the power we need to do it. Our efficiencies are, we've looked at the specific mechanical energy efficiency, and we're slightly better than a rotary bit or PDC bit.
All right, I'm staying with you there, Bill. On something completely different. Developing a new technology is strewn with uncertainty and unknowns, sometimes described by a good friend of mine as a drunkard's walk. Do you follow a structured development and validation approach to technology maturation? For example, at this side of the pond, we have a D&V technology qualification standard. Is there something like that in the US? Do you follow it?
Yeah, there are no textbooks on the technology that we're doing. In fact, I've been told by one of my board members that I need to write one. And so when we started this, we didn't know how it worked. We had seen some things in the laboratory that pointed us to the process. So the first thing we had to do was to try to figure out what the process was and how did it work, study the physics of it. And then our next step was to continue refine that, to refine the model and get to the point that we could then do laboratory tests. And then full size, full rate, high pressure tests, showing, taking it step by step to the point that we could demonstrate the technology. What was key is working with operating company and a service company to be sure that everything we were doing was well focused on the end product. Because at the end of the day, the only thing that matters is what a customer can use. I even went to drilling school. I may be the only pulse power engineer in the world certified to run a drilling rig. And that was very helpful to know what the real issues were and to stay focused on the end game.
Okay, thank you very much, Bill. Jan-Jette, you've only recently started Canopus, but you build on a decades of drilling R&D experience with Shell, as you said yourself. How does that affect your approach to technology development?
Yeah, thanks, Rob. That indeed must have a major impact on the way I approach these type of developments and things. I had a great opportunity to work in the labs where expandables, managed pressure drilling, and swellable packers, etc., were invented. And all these developments made use of great facilities that Shell had for internal projects. And I was thrilled to hear that Shell gave away these facilities to the research institute in the Netherlands, TNO, for public use. So that's what they are. They reopened the labs last February, just before the crisis, the Corona crisis. And in that context, I would like to mention three things. Before going for any challenging field pilots, etc., you have to de-risk and demonstrate to the stakeholders in a controlled environment like these facilities, and there are other facilities in the world as well, of course. But show it and de-risk it as much as possible, and that includes also the measurement of the specific energy that has been mentioned before, one of the key parameters. But also the whole cleaning and all the other stuff. And that brings me to the second point, always aim for an integrated field solution. Not the most complex one, so not the most challenging one, but the least viable product, as it is being called as well. Go for a simple one, but a complete one. So when you go to the field with a bit, make sure that indeed you get the energy there, that you avoid any potential damage to the well that is being given to you to play with it. And make sure that you have your well control story ready, etc. Last but not least, make sure that you have directional control. Without directional control, there is a very limited application of most hole-making technologies. And the third one is be selective on the field trial opportunities. So a badly chosen opportunity with a lot of tripping time, for instance, if you go to a large depth, etc., the cost will go sky high, and you learn only a limited amount of that, and also a bad prepared field trial with the crew that is going to help you out with doing the test can kill a technology already in its infancy, not because of technical reasons, but because of operational reasons. But one funny story about this, we once went to a rig with the software rotary system, which is mitigating the drill string stick slip vibrations. And very quickly the driller switched it off because the rotary became completely silent, or at least had a monotonous whatever sound, which is an indication that all the torque spikes were filtered out. which is the function of the technology, but the driller got nervous because this was not the normal sound of the system, and therefore he switched it off. Now that kind of things you have to prepare, and it is completely unexpected what you can run into after having spent so much time in the laboratory.
Okay, thank you, Jannette. Just staying with you there for a second. I'm going to be asking all of you this as I come back to you. Is how much energy does it take to remove the rock compared to rotary drilling with your method?
And then what systems do you compare?
Yours against rotary, conventional rotary. Pick your variety.
Yeah, no. So if in most works, of course, the PDC bits are the most efficient. If it's not too extreme in hardness. We compared the rate of penetration and the drilling efficiency, the specific energy, etc., with PDC and tricone bits, and we found pretty consistently that in every rock, after having selected the best bit mechanical bit solution that you could apply, that abrasive jetting is at least as fast, and if you optimize the energy to the bit, it is twice as fast as conventional mechanical drilling. The specific energy is a little bit less. That's about say 40% less. But the amount of energy that you can transport via hydraulics to the hole bottom is higher than for mechanical energy because of pressure restrictions in mud motors and other downhole equipment.
Okay, so thank you very much.
Yeah, okay.
Okay, Mark, same question for you, where Jannette comes from a very long oil and gas pedigree. You were a complete new entrant to the oil industry. I remember when we first met, we did a Drilling 101 day. What benefits and disadvantages has that given you as a complete fresh pair of eyes to this challenge?
Yeah, it's a great question. So I'm a unique hybrid. As I said when I first did my introduction, my background, I'm an aeroastro engineer with a master's degree from Stanford, and leading crew capsule development and spacecraft systems between Boeing and Jeff Bezos' company. And then my whole family's, I grew up in a mining town in northern Idaho, so going underground is sort of in my blood. I left conventional aerospace with this concept of finding a new way to fly. And I was 2 miles underground drilling with a crew, effectively, the deepest holes, diamond drill core holes in North America. And that's actually when I came up with this idea that you could take 2 miles of drill rod and do something special with what is amounted to a chemical railgun. And ultimately, that's what Hypersciences developed from, was an idea of merging an aerospace application with knowledge about that. And you're right, to start with, I other than managing drilling, I didn't really understand all the mechanisms. And quite frankly, we went and proposed this to Shell, saying we don't need to rotate at all. And in fact, we proved that we could get incredible rates of penetration by pulverization of both the projectile and the rock. So it has been, you call it a drunkard's walk to develop these technologies. I think it's really important to understand you do have a path. For us, it's betting on hypersonic velocity to do these really important things. And the fundamentals were actually developed in the 60s and 70s. It's just a matter of taking a technology like hypersonic ram accelerator that we use. It's a special technology, like it's a jet engine in a tube. Applying that to industrial makes us incredibly valuable as a technology, because in aerospace, you'll fly once, twice a day. If best, 300 rockets will take off a year. Today, there'll be 30,000 airplanes that take off and land because they depend on jet engine technology. We're only going to be successful as a company as we're flying thousands of these every single day in a drill hole. And that totally changes the paradigm for both industrial use of this as well as our aerospace use.
Okay, Mark, straight in one question from the audience there for you.
Yeah.
This stuff sounds pretty dangerous and stuff. Have you guys considered safety and well integrity risks? What are the risks of explosions, shocks, etc.?
Sure. No, absolutely. We've actually spent years working with what I consider one of the safest companies in the world, Shell. You start every meeting with a safety moment, and you start with safety briefings. We've actually gone through and vetted, and it's great to have as Shell and another major company. In fact, we're bringing on a few others into our field trials that are ongoing right now. But it's absolutely critical that you take safety first. We are doing something where we put all the energy down the hole, and it's a focused energy device, if you will. It's not an explosion. It's not fracking. You're actually firing a projectile. Think of it as an accelerator that's 10 or 20 feet from the face of the rock, and it brings that energy right to the edge of the rock and breaks that rock. So up on the drilling rig floor, you're not sending any materials down there that are inherently dangerous. They're independent until they're used at the point of use. So your diesel is actually down below, or your natural gas, your air is pumped down. Your projectiles have no explosives on them. They are plastic and concrete. So they're low cost, but they're also inert.
Okay, thank you. Igor, you wanted to make a comment to that?
Yeah, I think it's a very good point of making the difference between something that is in a laboratory and to go to the real practice and the field is the health safety environment. And I can say we spent last 2-3 years with this topic quite a lot, because originally that's the difference in this technology readiness levels, that something what you can ideally run in some test field or lab test that you can build, and then to be in a practical utilization regarding some vapors that could be created and to handle that. This is something very different, and also for us it was like some learning curve that we have to go through last years, and to be able to set up our solution that will be compliant with all health safety environment issues. Also regarding the team in a company, we have to build a specific team in a company responsible for all steps within the testing and development, and mostly going to the field. So I think it's one of the cornerstones of successful commercialization of the any new system that wants to do the things differently. And of course, last point maybe that we should expect, like all of us here, averse from the existing industry, that it's something new and different. So we have to double prove that our solution is safe and not bringing some big risks into the field.
Okay, Rafael, the next one is for you. Percussion drilling itself has been around for literally millennia, but it was overtaken by rotary drilling about a century ago. Air hammers have proven their efficiency in dry hole operations, and we're now seeing some clean fluid hammers with promising early results in some deep wells. And there's also fluid mechanical hammers in various forms, like the one by NOV. So there's clearly renewed interest in high interest from hammer drilling. Hammers are very compatible with existing drilling systems. They go on the bottom of them. They are used already in the field. However, hammer driven by a solids laden mud, as you guys have, seems to have evaded the industry for decades, with very much concern about erosion and dynamics. Why haven't hammers taken off and become mainstream already?
Yeah, exactly. I mean, I completely agree with you. You might call percussion drilling, the past of drilling rather than the future of drilling. Well, in fact, the technology has been around for years, and you can trace it, of course, down to air hammers, which are today used in a variety of applications, to water hammers, which have been around since 1985, 1990. But the big step is really to take these, which are hammers used in mining, in shallow drilling, and putting them in a downhole environment, deep downhole environment. You mentioned one of the key aspects, which is erosion, because now instead of circulating very pure water or circulating air, you're circulating a mud which is weighted, which has a lot of particles, which is not filtered correctly. So this was the first challenge in designing the mud hammer. And this challenge we overcame, I mean, quite early in the development. It's not something that's been the focus in the last, let's say, 5 years. On the other end, another aspect is clear, is that you need more fluid. So you need a hammer which is able to pass through a lot of the fluid. So this has been part of the research. And the third point is to design a bit, because you're not drilling with the same bit on surface and 5,000 meter deep. So if you want to have the same gain and to multiply the ROP, I mean, we're not talking about 30–40% gain like you have today with some of the hammers. When you're talking about high power hydraulic hammers, you're talking about multiplying the ROP by 2, 3, 4, 5, and that's what we've seen on the bench and in the first field trials. So it's a step change, and it required a whole new development, and it was a long road, but I think we are seeing the end.
Okay, thank you very much. I'll just stay with you, Rafael, very quickly. And an audience question there is, how do these new drilling tools work with MWD and LWD instruments? And for the non-technical outs there, that's measurements whilst drilling for directional control and logging whilst drilling tools. Does that affect you tools at all? And then we'll go to one of the radical new ones.
Yeah, I mean, you have two aspects, two questions here. The first is the impact on the electronics. Obviously, you're providing very high power impacts. So you're having, I mean, tremendous G's in actual shock. So electronics have done a lot of progress in the last years. And today we are able to measure, to have tools near bits, so very near to the bits, right under what the hammer is hitting, surviving or G's surviving our impacts and bringing us high frequency data. And that's something we're doing on a daily basis. So they do exist. I don't think today all the MWD and LWD are compatible. That's another question, but these technologies do exist and we've tested them. The second question is the directional behavior. This is largely untested because, to be frank, there's nothing in the literature that's about this. However, the tests are fairly easy, and it's something that we have set aside, I mean, a lot of time, and that we are probably going to tackle around the end of the year. We're looking at a budget right now to do this on a horizontal drilling bench and evaluate the directional behavior of a hammer by the end of the year. So it's a question we're tackling that hasn't been solved on right now.
Okay, thank you. Paul, the same question for you. Yours is even more out there. How does laser drilling interact with things like MWD, LWD, directional control?
Yeah, we integrate with conventional technology, whether it's really wireline, and our system's conveyed in coiled tubing, and we have, you know, fiber optic tools that are conveyed today in coiled tubing. And we're no different from that. It's just we are transmitting a lot more power down that fiber optic cable and using it to remove material to drill. So we even have tools today that are used for other applications where we've developed that type of sensors and telemetry and things of that nature.
Okay, and likewise, quickly, Mark, you've got a similar radical difference. How do you interact with LWD, MWD, and directional?
Yeah, sure. Our Houston-based team actually has a company called Kinetic Upstream now. They were some of the original developers of rotary steerable and have actually an annular system, electronic and control that they developed in our patents, as well as we now have them coming on as partners to help us develop the steerable portion of our drill. So it's very important for us to have something that allows transit of our projectiles and our accelerator through the middle. If you do want to do conventional pipe, you'll need an annular turbine, and we've worked through that design. If you're using coil tube, as Rafael pointed out, or Paul pointed out, it can get a little easier. But yeah, we have developed the tools and the electronics that are available today, both temperature and shock resistance. We actually put lasers and electronic instruments inside our projectiles, and they handle our start loads, which are way higher than any load that you see in any conventional system. So we're very confident with being able to run our electronics downhole in temperature and shock environments, and have done so in our testing.
Okay, thank you, Mark. The next one, I'll go to Bill first for the answer, and then we might go around the table. And this is a bit of a combination from various questions we see coming in at the audience side. There is, you might be able to drill on bottom incredibly fast, or at least as you define incredibly fast. But if it's too expensive overall, the economics simply won't tally up. Also, there are wellbore quality requirements. If the hole becomes unstable, it doesn't matter how good or fast you are, you're not going to get anywhere, so all might be lost. So as always, drilling technology is not just about moving rock fast, but it's part of the much wider requirements. How do you ensure your system fulfills all these needs? And people are also very interested in how fast you can actually drill.
Yeah, we have been quite concerned about wellbore stability from the beginning, and have been very pleased with our test results in very hard rock in the laboratory, that the texture of the wellbore is quite good, well defined, easy for casing. And I can't talk about how fast we can actually drill. Our strategic partner asked me not to, but it's quick. It's really quick. And so the managing the well has been an important issue for us for a decade, because at the end of the day, the product is not the drill, the product's the hole. And we have to develop a drill technology that our strategic partner can then manufacture and use to drill holes. So it's been a big issue for us from the beginning.
Okay, thank you, Bill. The next one is a bit of a combination there as well, from a number of questions. And of course, with all you startups, probably there's lots of questions out there on how much your cost per foot, what is your overall RRP, a lot of proprietary questions really that probably you can't put out there overall. Let me see there what we've got here. A question from the audience there says, oil and gas companies have spent big money to optimize drilling technologies and spending huge efforts on there. Some have abandoned projects in these very same areas after very large investments. Where will your future R&D funding come from for these new high-risk, long runway technologies for geothermal projects? Who wants to take that one on board? Mark.
I'll take it. I think it's great to have partners to help validate. Folks like Shell and this other company have helped us by being there. But if you have a technology that you want to bring to the field, it's important to have a very, very clear focus to demonstrate one thing and one thing well, particularly if you're a startup like us. So going fast and breaking rock, very important. We've found that you can go out and fund these things independently with non-conventional financing, and you should expect to do something. We heard yesterday, I won't go all into it, but you start out with the 4 F's: your friends, your family, and I think what are the, anyway, there's 4 of them, but it ends with you have to go out and seek enough capital to make these things work, to get to the point of critical field proof. I don't think the big companies, I don't know who wrote the question, but in general, people would like to see the technology sitting on the back of a pickup truck, and that's when they're ready to fund you. So get ready to actually get to that point. And that's what we're doing at Hypersciences, is actually bringing it to the field and funding most of this through crowd financing. So, Seed Invest and Start Engine are ways for us. We've raised over 10 million ourselves on crowd financing and are continuing to do that with Seed Invest.
Okay, Igor, you wanted to make a comment, respond to this?
Yeah, I see why also in general that why these innovations and these radical innovations in the drilling industry are not happening is that there are a lot of very big obstacles for new startups to create some ecosystem. We compare it with some other industries like, I don't know, IT or solar and so on. You see tons of companies that are trying to do something and something significant. And here we see the big obstacle is the financing and of course the time. So these are two connected things that to develop and then maybe mainly to prove the new drilling technology. It takes years. It is not a job for a few months, and also the expenses for building such kind of system and to have the test facility that you can prove it. It's a big obstacle. So also I agree with that. That first of all, also we started with some friends from family and angel investors and our own money. But soon as we knew that this is really significantly above our possibilities, we are able to combine private and public sources. But also our expectation now, in for example, for us in this phase, and we mostly used till now private equity or the sources for the new drilling development, and also industrial support in the form of some sponsoring on projects. Now we are also quite big in expectations from these green recovery programs that mostly here in Europe we see as a big potential that governments are trying to, at least verbally, to promise that next 2-3 years will be used. And I think is a big opportunity for geothermal to use it to make this step change. But also on the other hand, that it is quite a unique opportunity that I think the train is running, and we should be able to commercialize these technologies in next 2-3 years, because then the other not geothermal technologies, but the other combinations will have the momentum in this process.
Okay, thank you. Paul, you wanted to respond to this quickly, briefly?
I just wanted to reinforce that I think that's a huge challenge, particularly when you're talking about 10 kilometers and 300 C, and you look at the drilling efficiencies in oil and gas with how quickly it takes to drill an unconventional well. So I think that, you know, it's going to require some unique set of funding, and the traditional sources for game-changing technologies are gravitating towards other industries. I think if we want to see something for geothermal, it's going to require something unique, at least in the United States.
I'm staying with you there, Paul. I know I've got this for a few. People want to know in the audience how far you have drilled, how much money and time you expect to finalize to get ready for a field demonstration. And I understand some of you might be close there, some of you might be further away. So, Paul, will you be the first one to answer this?
Yeah, so the work we've done in terms of technology readiness level, we've spent a lot of time in the lab drilling your 4-foot blocks and come up with ROPs in the order of magnitude that are 3 times faster, and with weight bits and torques that are substantially lower, so less than 1,000 foot weight on bit, less than 150 foot-pounds of torque. So we've done the lab part of it, and then in the field part, we've conveyed to depths up to about 1 kilometer or so, and we haven't combined the two yet. With a proper program in place and sponsorship, we would probably be out there in the field to some depths in the next year or two.
Okay, Rafael, do you want to respond to this as well? I understand you've been looking for opportunities or something.
You mean opportunities for testing or for funding or what?
Field work.
Yeah, no, I mean, funding and testing has been the backbone of the innovation, and the ups and downs can be explained with the different partners we've had throughout the history. I mean, the whole project started with support from Shell, and Shell invested quite a bit in this technology in the early 2000s. Then Total took over the project. Again, that's all oil and gas DNA in the beginning, but the applications were so narrow that none of them came to light. And even though millions of euros were invested in this technology, in the end, we're seeing now the light with geothermal, which also some operators investing deeply into it. And I think we're seeing the end of this, and with the geothermal operators now. Keeping in mind, the most expensive thing is always the testing and the rig rates and finding the right well and the right opportunity to field test. That's what's been the pursuit for these 10 years.
Okay, Bill, for you, the saying goes, hardware is hard. You've been at this technology for coming on 20 years, I think, since 2003 you mentioned. How is such a time frame sustainable in today's rapid return on investment expectations?
That's a good question. When we first started looking at the drilling industry application for this technology, I had a very helpful conversation with people at Schlumberger, and they said it takes 20 years in the oil and gas industry to go from a new idea to a product in the field. And so we're about on track. We first had a private investor that funded the work to the point we could demonstrate it. Then an operating company got involved in it once they saw what we were doing, and then a service company got involved in it. And the industrial funding has been the key. And we have a very solid patent portfolio that we own, which is also key to it. And so the funding process has really been by the customers, by the people that need it. And they're the ones that have put the money into it and are continuing to do so.
Okay, thank you. Mark, one for you. Audience question.
Yeah.
Does your technique transition to large boreholes, and will there be stability issues?
Okay, yeah, so great question. We have developed a technology that offers you any variety of hole size. So for instance, the projectile, I know this one isn't spherical. This one I'm using right now, that's capable of drilling up to a 12.5-inch hole, with most of it being done with the hypersonic impact. What you're doing is you're actually shooting off center, and you're allowing the drill bit, that very outer annular section, to be drilled where you have the highest torque and your bit is most efficient. So that's how we maintain borehole control and what we call augmented hyper drilling. In the case where you're making even bigger hole, I mean, let's be honest, a geothermal hole is not just a drill hole. It's like a shaft, and it's more like a mining shaft. And so what we're doing is using these type projectiles to tunnel bore and shaft bore much faster and larger area. Turns out you can very reasonably control the outer perimeter even with your shot pattern, depending on the size. So borehole stability, very important. And while we can hypersonically have an order of magnitude increase in ROP, our real job is to have an order of magnitude decrease in overall cost of drilling and completing if you want to actually drive the cost. You can't just solve it in drilling. If drilling were free, geothermal is still expensive. So we work very hard to make sure that our systems are compatible with really low cost completions, which means, in fact, one of our patents is actually completing while you're drilling. So you're effectively building your completed hole while you're drilling, maintaining your stability all the way along.
Yeah, the same stability question for the spallation people. So either Bill or Igor who wants to, or maybe even Paul who wants to answer this. There's talk about glassifications or modifications to of the side of the wellbore that would even give massive benefit to wellbore stabilities. Who wants to take that question from you three? Igor, do you want to answer that?
Yeah. Well stability, in our case, then we are using plasma in a continuous or pulse mode. We are not vibrating. We are not changing anything substantial in a well. That's important in contrast to melting or evaporation when you are also influencing the borehole walls. Here, regarding the potential, how to increase even the opposite, like utilize it for the well stability, is that in specific regime we already had some smaller sub-project with one of the drilling service companies to be able to prove that we can seal or partially increase the stability of the walls. And it looks that it's a viable process, because it will be something like called casing while or sealing or casing while drilling, and that would be really another game changer connected with the drilling. And for us now, what is for at least for the first tests and the field trials, We are here strongly compatible with existing solutions also to keep the well stable. So as we are using all the equipment and the infrastructure conventional, it means that at least we want to make in a first step the same level as it is today.
Okay, thank you. Jan-Jette, for you. Are these techniques compatible with multi-leg horizontals, and are there life cycle issues like the equivalent of bit life?
Yeah, so of course, so the essence, I think, of all the technologies that are being presented here is that the hole making technology does not require weight on bit or torque on bit. And that means that the wear of the bit is primarily determined by the duration of the operation, and not so much by the interaction of the hole making method and the target formation. And this is kind of a bridge that the holy grail, I think, of hole making is finally getting a technology that not requires on weight on bit or torque on bit in the end. So longevity, if you look at the abrasive jetting stuff, the bit is touching the hole bottom, but you adjust the weight on bit in such a way that it is minimal and that the longevity is as long as possible. Other components, of course, you have to monitor a few specific wear parts, etc. But that is all that can be tested and controlled, and there's no issue there in that respect. And that will indeed also eliminate a number of disadvantages like tripping time on drilling rigs and cost reduction in that respect. And I expect that that's something that might be similar to the other technologies that are being presented now as well.
Okay, thank you. The next one, we will see who wants to take this one. What is the driving time to get to market? Is it the speed of the technology development, or is it scarcity of funding? Who wants to take this one, gentlemen? Rafael. Please unmute yourself.
Yeah, sorry. Been there, done that. I think we would all agree, and I'm ready to share views there. But one of the challenges in our industry is that it's not very easy to get testing opportunities and to demonstrate our technology in a real world environment. As I mentioned before, tests are extremely expensive. So unlike in electronics or in software or in other technologies which are extremely cheap to demonstrate in a real world environment, if we want to prove our tool works, we need to put it at the very bottom of a very expensive tool called a drilling rig and a drilling BHA on something that's already been costing millions to drill all the way down to 4,000 or 5,000 meters. And then show that not only our tool is not damaging the very high investment that's been made by the operator, but making him gain enough money so that it offsets the existing technology, which had the opportunity to get refined and better for years and years on these same rigs. So this is a high step, and this is what I find the most difficult in our industry.
Okay, thank you. We only have a few minutes left. There's a lot of really good questions coming in from the audience, I see, which unfortunately we won't be able to get to. But let me wrap this up. These 6 technologies are all very different in how they remove rock, but are all subsystems in the overall drilling system, where you all share a joint. Let me go back to that. Your 6 technologies are all very different in how you remove rock. But are there subsystems in the overall drilling systems where all of you have a joint need? And I'm thinking of, working in the ultra high temperature, ultra high pressure environment. Are there needs in none systems, and etc.? How reliant are you guys on developments in other areas? And what can the wider technical, economic, and political environment do to improve progress for you? Who wants to take this one? Bill, and then Mark.
The high temperature of the geothermal environment is a big issue for us, and we are actively working with NREL under an ARPA-E contract to develop switches, capacitors needed for the geothermal environment. So the high temperature electronics are a big deal for us.
Okay, thank you. Mark?
Yeah, I think I agree that the temperature environment is a common one. I think with, and I know this isn't about the completions, but without drilling being compatible with low-cost completions, you're just solving a small part of the bigger problem. And yes, geothermal traditionally today could be 30 to 50% of your cost could be drilling, but completions, combining the two is, I think, critical.
Okay, Jan-Jette, you wanted to add to this? And then Igor.
Yeah, just on the measurement well drilling or the surveying sensors that you need for the correct well placement. When temperature increases, then the accuracy and the precision goes down quite dramatically. And for some of for many of the geothermal systems, you need with multilaterals and whatever, you need to place the well in the right place. So these high temperature, reliable surveying sensors will be important.
Yeah, I think, Rob, the one thing I was bringing up, when we fire our projectiles, you actually get an acoustic signal where you can see downhole what's going on. So it's very important to help your completions as well as your knowledge.
Okay, Igor, you wanted to add something?
I think I agree with colleagues, and one absolutely big non-technical problem that I think is for all of us is the communication. So here it doesn't matter if we are talking to investors or to the politicians or to the funds that are available. The lack of knowledge of the geothermal potential, and specifically to all of us, like we are opening something totally new. And I think what I hear listen is an ambition. And what I see now currently also in Europe, I'm not so familiar in the States, but I see similarly, is really the clearly articulated ambition of the industry to bring the disruptive solution that can bring totally new financial, economical, and energy market for the companies, like, for example, also oil and gas. We call it here internally like switch to clean. And this is, I think, one of the very important points that is a challenge for next years.
Jan-Jette, you wanted to quickly add and respond to this? Very briefly, please.
Yeah, a very quick one. Indeed, the funding and the opportunities to pilot the tests, the technology is extremely important. There are many subsidy schemes at least in Europe, that you can make use of or try, but these are lengthy processes and take at least a year. And it would be great if there is a much faster way to get these funds available if you have a good plan.
Thank you very much. I'm afraid we have only a minute left, gentlemen, so I would like to thank you very much for your time. Time has flown by as usual. For all the questions, and anybody in the audience out there that thinks you've got something to add to these people, something to contribute to them, all 6 of them are on LinkedIn, so please go and fill their boxes for them, offer them your services, and let them know how you can help them get their technology to market faster and cheaper. For all the other stuff that we didn't address today, for the hot wells that we need to be drilling in the near future to make these wells faster and an awful lot cheaper, tune back in tomorrow when Kate Young will address the future of wells, advanced tools, techniques and methodology. That's the first session of tomorrow at 10 a.m. Central Time. But stay around now, because in half an hour we have some real heavyweights on board. We will have, moderated by Peter Terzakian, we will have a surprise panel consisting of James Dupree, former COO, Global Subsurface, Global Projects and Exploration of BP. He's only formal because he goes and retires after he admitted to this project. We have Michael Lieberreich, Chairman and CEO of Lieberreich Associates, heavyweight in the financing, and we have Carl Pope, no one less than the former chair of the Sierra Foundation and currently principal of Inside Straight Technology. So stay around for more fireworks in Pivot 2020. Thank you, everybody, and see you next time.